Hello and welcome to Fixing Poor Database Patterns in Azure SQL Database Applications. I'm Martin Cairney and I'm the Associate Capability Lead for Data at Telstra Purple in Australia. I'm a Data Platform MVP for the last 6 years, a Microsoft Certified Trainer. My contact details are on this slide, so feel free to reach out to me after this session if there is any further questions and clarifications you need. My background with SQL is I've been working since the end of the last century with SQL Server, from version 6.5 all the way through to 2019 and onto the Azure PaaS offerings as well. So what we're going to talk about today, Azure SQL Database, it's just SQL, isn't it? Everything is the same between your on-premises and your cloud databases. Or are they? There's still some important considerations that we need to have in place, particularly in the cloud where you can't guarantee the placement between your application server and your database server. When it's your own data center, yes, absolutely, you can set them up in the same rack, virtually no distance between them. Great latency, great performance through that. But when it is in a cloud data center and you've got no control over the positioning of those servers, there could be quite a distance between them. In my experience, running an upgrade many years ago for a customer, the original servers were both in the same cabinet. However, as we were only upgrading the database server and leaving the application as it was, we only moved the database server to a new rack. Now that happened to be on a completely different floor of the data center, quite a distance away. We found that there was issues with the latency and the bandwidth between those two servers. So that can be very important and something we obviously want to make sure that we consider when we're architecting our Azure SQL database solutions to make sure we minimize anything that we can in terms of the performance degradations. So what this session is going to cover is really the top 5 that I see in terms of how we can optimize the usage of the resources we have to maximize our database performance. They may not be the same as your top 5. There may be some aspects in this that you don't experience in yours. All great if you've already addressed them, but let's be aware of them so we understand what we need to look for. The first aspect I want to consider is the firewall. Now you may not be aware that there is a couple of options for the Azure SQL Database Firewall. It's something that isn't commonly known and commonly understood, because what I almost invariably see everywhere I go is the application set up, connecting onto port 1433 to the database in Azure. Now that's quite simplistic because what actually happens is you connect to the Azure Gateway. That accepts your connection on port 1433, but then what it does, because your database can move between servers, by default you have 3 copies of your database that are kept in sync across different servers. So which one is actually active at any point in time? That's what the gateway keeps track of. It understands which server your database is currently running on, and when your connection request comes in on port 1433, it translates that, determines which server it's actually going to connect to, and passes your connection through to there. But that proxying remains in place. So how can we improve the latency? Well, one way to do that is to change to a redirect. Now your initial connection still goes to the Azure Gateway and still goes on port 1433. But this time the gateway returns back to your application the actual direct address of the server that you're connected on. It does translate it into a different port range though, and that's the important thing that we also need to consider. That 11,000 to 11,999 port range is something that then has to be opened all the way through. So opening those additional firewall ports needs to be done at all levels. Starting from your application server, if that's running on Windows, making sure that Windows Firewall allows the outbound ports, right the way through to your corporate firewall if you're running on premises and sending it out over the internet to your Azure SQL database. All of those need to be considered, and all of them need to allow the port range. Now it has to be that entire range because there's no way we can identify in advance exactly which port it's going to be running on. It could pick any of those. Also, the gateways will change. So if you're setting up your corporate firewall and allowing in the allowed list of IP addresses, you need to make sure that is kept up to date. It can change over time, so make sure you're considering those and passing everything through. As I said, all levels of firewalls need to be considered. Windows, NSGs, any other firewall that you might have in place between your application server and your database server. If you've set up your SQL Server connectivity to use the VNet endpoints and granted a certain VNet permissions to connect through as the SQL Server property, that still needs to be configured to allow those additional ports through as well. It isn't automatic just by allowing the SQL Server endpoint. You still have to open the firewalls. Now, one other thing to remember and to consider though, the additional latency that you might have just because of the location of your application server and your database server might be so significant that any gains you get from changing to redirect may well be swallowed up. But in some cases it can be enough of an impact, and if you've got enough in the way of connections coming through that regularly need to make a new connection to your database, it can end up being a saver for you in that sense. Until recently, the only way to change this was through code. You either had to write a PowerShell commandlet or use the Azure CLI or similar to make the change into the connection property. Now they have exposed that through the portal as well, which makes it a little bit simpler to make the change and to verify what is actually in place. Another way of verifying it is if you use a network analyzer like Wireshark. When you track the traffic through there going to your SQL Server from your application, you'll actually see that explicitly of it changing the address that it's aiming for, and the port number will change as well. So it will go from 1433 into something in the 11,000s. So let's have a look at how we do that. And we'll have an example on here of setting up proxy and setting up redirect. And we'll do some simple querying over it and track the latency that's introduced and see how that's impacted over time. So when we come into the firewalls and virtual network section of our Azure SQL Server, here's where we can see how our connection policy is currently configured. You can see both the redirect and the proxy options are available there. Default is exactly the same as proxy. So at this stage, we're currently set up to use the proxied connections. The other important thing that I need to consider is my network security group. And if I jump into this one, so this is controlling access from my client VM, which is just a VM in Azure that I'm connecting to the databases with. And I want to look at the outbound security rules that I have defined for this environment. I have my straightforward SQL Server on port 1433, so all of my outbound connections to any database server should be allowed. I also have an additional redirect rule, which is my 11,000 to 11,999 port range, and that's controlling whether that high range that is needed for the redirect connection type to work is enabled or denied. So the first thing I want to show is that we do have the correct settings enabled. So I run this and it's going to show me what my connection policy currently is for the SQL Server. And as we can see, as we saw in the portal, it's set to default. That's all very well, but for this demo, I want to be explicit about this. So I want to confirm that it absolutely is proxy. So let's set it to proxy from the default and confirm that that's in place. So we now have our connection type being proxied. In addition, we need to make sure that our NSG is set up correctly. And again, I want to show that initially the additional NSG rule is set to deny. So we've only got port 1433 enabled as our only outbound connection. So this now confirms as the output from that the high range ports are blocked through the NSG. So we'll jump across to my client VM. So this is running in Azure in a virtual network which is controlled by the NSG. So first of all, I want to make a connection to my database. So let's hook in there. And once we're connected, we're just going to run a nice simple query. We'll use this query to test the latency response from the server. To do that though, I need to switch on the include client statistics option here, which is a nice part of Management Studio, which gives us some more information around the query performance. So we'll let this run a couple of hundred times to get a more representative sample of the latency, just to build it up so that it's not down in the single digit milliseconds. We want something which we can actually work with. So when that comes back and we look at the client statistics, what that shows us is that the wait time on server replies is our indication of latency. So in this example, it was 812 milliseconds over that 200 queries. So let's keep a note of that. 812. So jumping back to code, the next bit I want to do is change my connection policy and now set it to redirect. So we'll run that and we get the confirmation back from that it has changed the policy and we're now using a redirect. However, at this point, I haven't changed the NSG and I want to show you what impact that can have on the connections. So let's establish a new connection to our SQL Server. Now this time, because we've got the redirect switched on, it's going to first of all try and make the connection on 1433 to get the information about where to redirect to, and then try and make the connection in that 11,000 port range. But because we haven't enabled the NSG part of that, it can't get outbound on that port range. So it's stuck. It's not able to make that second connection on the direct part back to the database engine. And what we will end up with is a timeout. As you see, it's timed out because it's not being able to make that connection through. So we need to jump back to code and update that. And the way we need to resolve this is now to enable the redirect NSG rule so that we can now get the traffic on that higher port range. So we've got the confirmation there that we've now allowed that NSG rule and it's in place. So now when we make our connection, because we've got the new port range open and the NSG enabled, it should be able to connect correctly. So I'll now go ahead and run exactly the same query on my redirected connection. Again, put the client statistics on and we'll gather that information at the end. So the nature of the query, I'd expect that the overall duration will be much similar and we should only be within a few hundred milliseconds of a difference on the overall performance. So when the client statistics returns for this one, we'll bring that up and zoom in on that. We'll see that the wait time on the server replies is now down to 469 milliseconds. So we can see we've got quite a significant saving on the wait time on the server replies there, indicating that our latency has improved quite significantly. The overall query time hasn't really shown much difference on this one, but you can imagine over larger queries, greater processing, more frequency, more number of client connections, that this could have a major impact. The next area of consideration is looking at overfetching, commonly known as the n+1 select problem. So what is the n+1 problem? The n+1 problem is typically found in ORM style applications. Where you've got the framework generating your SQL queries, it can lead to some odd behaviours. Generally where it's manifested is when you have one-to-many relationships defined in your database or in your model, more appropriately in the application code. From that, you tend to want to select perhaps one item from the parent table. However, you then need to get some of the properties or some of the columns from the child tables as well. So that the way the code is generated for that is that it'll do one select from the parent table initially to pull back those records that satisfy the main criteria. Then for each of those, it will go back to the database and get the related information from the child table. Hence the N is however many number of records are pulled from the parent table, plus that one query against the parent table itself, giving you the N+1. So because we tend to have that higher latency in our cloud databases, anything that involves the more return trips to the database than is actually needed is going to have an impact on our performance. So instead of being able to just go once to the database, pull back all the information that we need, we're getting unnecessary calls to the database numerous times and hence the slower performance. Another common manifestation is perhaps relying on APIs. Your application calls the first API and that returns the core part of the data, similar to the one in the N+1 manifestation. So that data comes back and it's got most of the data that we need to satisfy our query. However, we still find that there is still additional pieces of information that we need. There's another API and that API provides the remainder of the information. However, yet again, because it is intended to just respond to a single request, you've got to call it multiple times to get there. So having that dependency and going, we have to use this API to get our information, can again be another way of having those issues of too many calls to the database. The resolution for it though can be quite simple. It does need to go back to the application code, but having a look at that and where you've been able to identify it, perhaps by seeing repeated queries coming through in the SQL Server side that suggest that that is probably what's going on, you can look at different ways of changing the code. If you want to keep your ORM based approach, some of the options are, for example, in having the .include part, and that's explicitly instructing the code and the ORM generator that when it goes to the database to get that information from the parent table, include all the information from the child table as well. The downside on this is that perhaps you're bringing back all of the information from the child table at that point. Another way might be to be explicit about it. So instead of relying on the ORM to generate your query, you might write it up as a stored procedure, for example. That way your code can call that and get back only the information it actually needs. So let's look at a demo around how we can visualize the N+1 problem and see the improvements that can be made just from the simple code change and remove so many round trips to the database. So to demo the N+1 selects problem, I have a console application which will query a database where there's some related tables. What it'll do is do one version with the N+1 code in place and another version with the fixed part. And if we look at the difference in the code, it's actually quite subtle. There's not really a great deal of difference in it. What we can see, based on the main bit of the query generation on this side, on the N+1 side, is that we're querying the standards table filtered by certain teachers. What we then do though is say that for each of those standards that are returned, I want to get some student information as well and get the student name. When we look at the fixed version, what we see is that we've added in this .include of the related students. So in this point, what happens is it will query the standards table, it will join it to the students table and pull back the related students information as well. The remainder of the query is exactly the same. It's still looping through for each standard and getting the outputted information about the student name. So let's have a look at how that actually runs. So my first attempt here is the N+1 version. Now what we can see from here is there's several queries being executed against the database. The first of those, after we've opened the connection, is querying the standard table filtered by the particular teachers that we've applied onto there. And we can see that that on its own took 21 milliseconds to execute. We then have these additional selects. So these are the n's in the n+1. The first query up there would be the +1. And these are now the n's, which is saying that for each of these entity key values, so the standard ID that's come back from the first query, go to the student table and get the related information from there. And what we see from that is that we've got something in the sort of 20 to 30 milliseconds for each of those. So with the number of records that have come back from the first query, we can see that we then run an additional 4 queries to get the remainder of the information. When I compare that to the N version only, we can see that there's only a single query that's now been generated. Now it is a bit more of a complex query, as we can see, but when we drill into that, what we find is that we're now still doing our select from the standard table, but we now already have a join in place to the student table to pull that information back as well. The benefit of that being that the total query now has run in 23 milliseconds. So it's not really much of additional overhead compared to the first part of the previous n+1 query. So you see that when this generates and when you do get a large number of values coming back from the first query, it can severely damage your performance levels. Another aspect of resource limitations with Azure SQL Database is that we often have restricted memory. Particularly when you're using the DTU model, because that's a blend of CPU memory and IOPS, you don't know exactly how much you're really playing with there. So the best thing for performance is to make sure that you understand how your applications are using the memory and making sure that is optimized to get the most from it. And your planned cache can be one of those areas that, if you're not careful, can start to consume a higher percentage overall and impact how much is available for your data cache. So as a reminder, when a query is submitted to SQL Server, first of all, it will go through the query text itself and create a hash from that. It will use that hash to then see, is there an existing plan that matches that same query hash? If there is, great, it doesn't have to do anything more. It knows how to undertake that query, so it will reuse that plan. If the hash doesn't match, however, it's then got to compile a brand new plan, and once that has been compiled, add that to the cache, and then it's able to execute it. Some of the aspects we need to be aware of, though, around the plan cache is that there is a limit to it, either by the total number of plans or by the total amount of memory that it consumes, whichever is reached first. And that will vary depending upon the tier that you have, so how much resources are actually available. The text coming in that gets hashed needs to be an exact match as well. Having spaces in it, in your query, having a new line, splitting your query over multiple lines, can actually change that and mean that it won't actually match the query hash that's there and existing in the cache. So be aware of that as well. Be careful how that is generated. As I mentioned, a higher amount of plan cache can result in lower buffer cache, meaning perhaps greater IOPS in your database when it has to get more data from disk rather than being able to serve it from memory. Another one, which is often linked to the n+1 problem that we mentioned in the previous section as well, is that you could end up with a very high number of single-use plans. So if that the n side of the n+1 is pulling back very specific information, passing in a key value there to extract single rows, for example, as that changes, that can actually be seen as a completely different query each time and generate a new plan. And when we don't have a plan that we can reuse, the query cost in CPU terms of having to compile or recompile that query, again that can lead to performance degradation. So when we see the high CPU from compilations and the high memory usage from planned cache bloating, it means that there's less DTUs available for actually running the queries. But we can fix a lot of this, and a lot of it can be fixed relatively easily. We want to make sure that the queries we're sending can be parameterized. If there's less variation in the text, where the only bit is just the parameter value itself, then that leads to a much higher reuse and obviously better performance. Some ways we can help to nudge that along is by maybe setting parameterization to be forced, in which case every query is then attempted to be parameterized, and you may end up with a greater cache hit ratio out of that. There can be some downsides to that, with parameter sniffing becoming involved. The other way to do it is perhaps looking at optimizing for ad hoc. So if you know that your workload does come in with a lot of single-use plans and does retain that pattern from your application, then setting it up with optimize for ad hoc reduces the amount that's in the plan, because the first time it sees that query, it's not going to store the full amount. It actually has a much smaller footprint in memory, which can lead to more plans being stored in your cache and better reuse of that. If it's never seen again, we don't get a full plan stored. If it does, so if it's proven it's actually useful and being repeated, then great, we can get a plan that's stored for that one and ensure that we have the best reuse. So let's have a demo and see how various queries and different levels of parameterization can lead to differences in the plan cache. So let's have a look at how the plan cache can be impacted by the patterns of queries that you might use. The first bit we're going to compare with is around the parameterization side of things and how that impacts the plans being stored in the cache. I've got two queries here, or two stored procedures, that are going to do effectively the same thing, but do it in two different ways. My first one, my unparameterized selects procedure, is using dynamic SQL, and it's building up just a straightforward query to execute against the database. Now, this is a terribly convoluted example and not something you would tend to see in real life, but for the sake of the example, it will demonstrate what can happen. My second stored procedure is my parameterized ones. Now, it builds a proper parameterized query at the end here by passing in a parameter that we've built up and passed in earlier on. So let's go ahead and create those two stored procedures in our database. Now, the first thing I want to do before running into this is clear out the procedure cache, just to make sure that we've got a nice baseline to start from and everything is cleared out. And let's verify that. Let's run this query to check if there is anything. So we can see we've got a clean plan cache to start with. So the first bit I'm going to do is run the unparameterized selects, and I'm passing in 10 as the number of times to do this. So it'll basically do 10 lots of the query within there. So say that runs through 10 times, and we can say it's doing roughly about several thousand rows each time on there. So now that that has run, what's it done with the plan cache? So let's have a look and query that. So what we can see is we have one plan in here for the procedure itself. So that was our defined procedure that we created. And then for each execution of it, we can see that we have another ad hoc plan that's been created. And we can see the full details of the plan in here and everything in there. We can scroll out the actual query text so we can confirm what's happened in there. And we can see what's happened is that it's built up the string with the actual parameter value and put those in. So we can see there's no parameterization on this. Each one of them is different, which is why we get the 10 plans in there. Okay, so let's now do the same thing with the parameterized selects. So again, it's doing much the same amount of work. We'll be getting several thousand records each time it runs through there. But now, when we come in and actually check what's happened to the cache, run that same query again to rerun that. Now what we can see from here is that we still have the procedure in the same way as the previous one, but now, rather than the first procedure where it was never actually executed, it was the individual commands that were executed one time each, we've now got on the execution count for the new stored procedure, it's been executed 10 times. So it's had the reuse of that plan. It was able to use the same plan each time. So let's clean up our cache again. And again, we're going to come back and rerun our unparameterized one 10 times yet again. Once that completes, again, we'll go back to verifying what's in there. Again, pretty much the same as we saw before. So now what we want to do is create a brand new connection. And within that, we're going to grab some of this text and run it through. So let's grab that, drop it into our new query window. So first of all, we're going to set parameterization to be forced at the database level. Now when we run our unparameterized selects again and go through and verify what's happened to the plan cache, what we now see is we now have a prepared plan for that. It was executed 10 times. And then when we extend out and look at the query text, what we see in here now is that it's forced that bit. It's identified that we could parameterize the state, and it's done that and determined what to put in for it. So we can see from the start here. Great, so that has found one way where we can actually save on some of the plan cache usage for that. So let's reset things back there, and we don't need that one anymore. So the next configuration we want to look at is the option to optimize for ad hoc workloads. So let's switch that on for the database, and again we'll clear everything out to give ourselves a fresh start. Now the optimize for ad hoc workloads, as we mentioned, we're going to see it that it will record only a partial plan for the query as it comes in the first time, and only then once we see the reuse and see the extra value for that query will we then see it being able to pick up additional plans. So let's see what our starting point is. We'll query what's currently in the cache. So let's grab that. I'm going to take a copy of this and paste it in here because we're going to come back and refer to this. So let me just tidy things up a little bit to make it a bit more readable for us as well. Okay, so now that we've got this bit to start with of what's there, let's actually run some of the ad hoc queries and see what happens throughout that. So we'll pick one, let's run that, and we only need to run it once. We just want to see what happens whenever it comes in the first time. So now when we come and have a look back in the plan cache, what we have is our compiled stub. The biggest bit we see missing there is we don't actually have the full query plan stored. but it's still got the remainder of it. We've still got the query text. It will still be able to identify that from the query hash and be able to see that it's the same query coming in again if that's what happens. Now we choose a different value. And again, we'll come back in and see what that's done into the plan cache. And once again, that's created a plan stub. Again, no full plan recorded with it because again, it's a different query. It's still that single use at the moment. So there's nothing to make us record anything further. Now if we go back and do that first query again, and when we come in now, we can see that it's changed. We'll see that that initial stub from the first query has now become a full plan. And we now have that full plan stored. And because it's changed, our execution count has reset back to 1 for that. So let's see what that does now within the details of what we've stored. Now I want to scroll back up again to the one that we did at the start so we can have a comparison. So what we see is our ad hoc plans have increased as we expect. We've ran 3 queries. They've counted up there. Our single-use plans, again, have come up by 2, matching what we saw from the queries that we ran. So what happens? What is the growth like when we start to see this of an increase in the number of single-use plans? So we'll rack it up. Instead of just 10 times, we're going to run this for 100 selects. So we'll probably get close to almost 100 random entries in here, so 100 single-use plans. So once that's done, let's have a look and we'll see again how that's impacted the cache usage. So we'll just let that one finish. Okay, and we'll go back and compare that to the start again. So we can see from this that our total number of ad hoc plans has increased by about 100. So that matches the number of executions that we did through the store procedure. If we look at our single-use plans, they've also gone up, but not quite by the same amount. And that's probably suggesting that out of that random numbering or that random parameter generation that we did within the store procedure, we've perhaps overlapped a couple of them and actually reused the plans on a couple of occasions there. What we can see though, interestingly, is it has helped to bring down the amount of storage used by single-use plans. There's been a number that have gone through there and been able to be reused. But our total plans, our total storage has gone up through that as well. So we can see that that's a small amount of hit on there, but it has generated some growth in the amount of plan cache consumption that we've got. And we can also see the numbers in there start to blow out as well. So let's reset that before moving on to the next one. So the other area where there will be an impact is on the number of compilations and recompilations. So let's create a little experiment here so we can see how that is impacted as well. Once again, we'll clean everything out to start with. So I need to create a new query here for for the store procedure run. And this time we're going to run about 225 times. So each run is going to take about a minute. Now while it's doing that, what I'm going to do is track some of the performance counters from SQL Server and from the system level there. So I'm going to put this into a loop, and within that loop I'm going to grab the compilations per second, the recompilations per second, and I'm going to grab that every second as it runs through. So let's start things off. So I'll come over and we'll start this one first of all, and then while that's going, let's start gathering our compilations and recompilations for the performance counters. So as I said, this will take about a minute to run, and for the sake of brevity on the recording, we'll catch up with this once it completes. So our collection query has now completed, so let's jump back and cancel the execution on this one. Okay, so we've done that for the unparameterized selects. Let's do the same for the parameterized ones. So we get a nice comparison there on the number of compilations and recompilations per second. So again, we'll start this one executing off. And again, we'll come back and do the same. We'll put this into a loop and we'll gather the performance counters while that's running again as well. So again, it will take a minute for the sake of the recording. We'll come back once it's completed. So our collection is now completed for the parameterized selects, so we can cancel out from here. So to analyze the comparison between those, I've got a Power BI report which is hooked up to my performance counters table. Let's refresh the data from that latest run and see what we get. So if we look at this, the rate through on the unparameterized query, it's certainly churning through and doing a great number of compilations and recompilations through there and gathering that information. Whereas we look at the parameterized version, and it did virtually nothing the whole way through. We hit one point here where it had to then do some little bit of recompilation on there. So you can see that that whole churn for the CPU on the compilation time is going to be so much better if we've got proper parameterization on our queries. A further way to optimize our memory usage is to consider compression on our data. Now this works now on the buffer cache rather than on the procedure cache, and allows us to have more data pages into memory at any one point in time. There are a number of types of compression that SQL Server supports. Column store indexes by their very nature are compressed, but they're always compressed and there's no way that we can change that. There's the compress function, which can take some data, apply the gzip algorithm on it, and store that. Now the downside of that is limited indexing is available onto it, so it's not really great if you actually want to be searching for values within that data. The better ones that are available to us that still retain the sargability are row and page compression, and they're the areas that we'll be focusing on for the rest of this module. Row compression changes the storage format, so it's quite simple changes in just the way the data is actually stored across the whole row, but that can lead to some savings. Page compression then does a replacement pattern across the data that's stored on the page. So it starts to look for repeated patterns, pulls those out, and stores a code for them instead. So with row compression, anything that was fixed length storage will be switched and stored as variable length. Nulls and zeros are even better because they can actually be optimized to take up absolutely no space in the row. So if we look at an example there on the table, the comp table, our first column is a big int, our second column is a 30-byte character. Now if we put values in there that don't actually go beyond the boundaries of the next level for the numeric values and are less than the 30 bytes for the character values, we can see that we get a reduction in there. So for the value we're inserting, we find that we can reduce the numeric storage down to 2 bytes. And with the length of that string, it will only store 24 bytes to cover that. There's a saving just on that simple example of 12 bytes per row. If we assume there's 1 million rows on that table, we can get about 30% savings in the size of the rows. Allowing us to put 30% more pages into memory, you can obviously see the great reduction in I/O that you might have from that for the physical I/O. Page compression is a little bit more complex, so it starts with row compression. So we always use row because it will give us some savings generally in almost every scenario. Page compression only really works though when there is a lot of repeated patterns on the page where we can get that. High cardinality doesn't work particularly well with page compression. So what it'll look for first of all is it looks for prefixes on the data there. Where it can find those common prefixes, it will pull those out, store them in the header, and replace it with a code value in the actual row itself. So we can see that first example in the first left column. It's identified that there is the string AAABCC that it can pull out. However, that first value only has the same characters in the first 4 columns. So in this example, it stored 4 as saying it's taking 4 of the prefix from there and then leaving the other one behind. Where it's got an exact match, it's able to store an empty string on there as well. Once it's done that part, it then moves on to the second phase and applying a dictionary compression. So on the remainder of the page, it will then start to look for the repeated values and be able to pull those up and map them up as well. So obviously, compression is going to allow us to store more rows on each individual page. There will be more rows, therefore, in the buffer pool. There will be fewer reads needed to satisfy a query. And that can lead to higher page life expectancy as well. So if our page is staying in the cache longer, it reduces again the need to go back to disk and extract it out again. We do need to look and see, across your pattern, what's your workload like and is it worthwhile adding in compression as well? So if you only get few duplicate values in your column, row compressions are going to be the way to go. You're not going to get any great value going to page compression above that. If you have a low percentage of updates relative to the total operations, then page compression could be of value as well. If there's also a high percentage of scans relative to the total operations, so either a low number of updates or a high number of scans, again, you're going to get good value from page compression. Be aware though with heaps, although you can compress the heap, new pages added don't automatically pick up the page compression until you actually do a rebuild. And rebuilding a heap obviously implies putting a clustered index over it and then dropping that again to actually rework the data. So just be aware that that won't necessarily pick everything up by default. It's also only defined on the clustered index. Any non-clustered index are individually defined, so they are not necessarily compressed at the same time and using the same algorithm or the same compression level as the main table itself. And it's not available on log pages. For log pages, if you really need to pull those down, you might look at the compress function and see if that gives you any benefit in there as well. But nothing comes for free. There is also a corresponding increase in CPU cycles because it now has to decompress the values as it reads them off the page before it can return them to satisfy your query. But generally, because IOPS are far more painful than CPU cycles, you'll generally find that you get a better performance overall by having compression available when it suits your workload. You will also have an impact once you do actually deploy it. Because there's a different pattern, your query plans will then be invalidated and it'll have to recompile for those the first time round. So again, there's that small hit on startup, as it applies that small ongoing hit from the decompression with the CPU cycles, but the benefits you get are many, many more pages held in memory for longer and giving you the benefits that way. So let's have a look, and we'll do some evaluation in this demo to see what benefits compression is likely to give us and some actual returns from that, and seeing how does the queries perform with the varying levels of compression in place. Okay, so let's have a look at how compression can help with our performance in the database as well. So first of all, I'm going to gather a baseline. So first thing I'm going to do is make sure I switch on my actual execution plan. So I'm going to get some statistics information out from there. We'll clear the prop cache and select from our order line table here. And we're going to use that as our baseline. So once this completes, we'll see what the actual performance was, and then we can do the same comparison with the compressed versions of the table as well. So let's bring up the properties in the query plan. Let me drag this out so we can keep it pinned out here. And the first thing I want to do is just grab some of the time stats that it took for the whole query there. So we've got the actual CPU time as, and the elapsed time as well. We'll grab that. Let's pin this to keep it up. And then from the actual select, let's grab the I/O statistics as well on the number of logical reads. Cool, so we have our baseline here. So the next thing I'm going to do is go ahead and actually apply row compression onto this table. So this will take about a minute to run, so we'll come back to this once it completes. Cool, so that's now completed. We've now got data compression, or row compression on our table. So again, we're going to repeat the same query, and then once that completes, we'll grab the same statistics information from the performance level of it and see how that compares with our baseline table. So once again, let me grab the initial properties for the time. So we'll get, again, our CPU time. And the elapsed time. And then from the actual select part, again, we'll grab the logical reads. Next, we'll go ahead and apply page compression onto the same table again. So again, this is going to take about a minute to run, so we'll let that complete and then come back to it. Cool, so we've now completed that of rebuilding it with page compression. So once again, I want to go ahead and do the same select again, this time from the table with page compression in place. And again, we'll grab the information at the end of it in terms of how that's performed and do another comparison. So we'll grab the logical reads. The CPU time. And the overall elapsed time again. Okay, so let's have a look at how they all compare. So if we go back to our baseline, we had just over 12,000 logical reads. When we come in with row compression, we've managed to bring that down to just over 10,000. So getting close to, almost, I guess, a 20% decrease on there. When we're looking though at the CPU time, it goes from 1400 milliseconds up to about 1800. So there's a little trade-off there on the CPU time increasing. However, when we look at the elapsed time overall, we see that there is very little difference in that. So it seems as though, yes, there is an increase in the CPU time as a result of the extra CPU cycles to decompress the data. However, the trade-off in that is by having fewer pages to have to do that on, the time kind of balances out overall. So we've definitely got a great improvement on our IOPS, and where IOPS are perhaps one of our biggest constraints, then that's going to be a great win for us out of that. However, let's see what happens when we move now on to page compression. Again, we're going to compare it back this time to the row compression version. So again, we've got a further decrease in the number of logical reads. So we've done well there. We've got about another 20% decrease in the number of logical reads. So that's pretty good. And again, we see the same sort of pattern that the CPU time has a bit of an increase as well, where it goes from 1800 milliseconds to 2300 milliseconds. But again, our elapsed time hasn't really changed by the same amount. It's still in and around about the same bounds of close to that 15-second mark. So once again, we can see that we've managed to get a great improvement in terms of our IOPS. We've had a corresponding increase in the CPU cycle time, but the overall impact hasn't really changed the duration of the query. The final section I'm going to talk about is looking really at resource governance. So because of the shared nature of SQLDB, you don't have that dedicated server to yourself. You have to play nicely with everybody else that might be sharing the physical resources. So to do that, Microsoft have implemented effectively a resource governor across your Azure SQL database. And it is pretty much the same as resource governor would work on an on-premises SQL Server instance as well. So the IOPS limits are, as I mentioned, they're set there to reduce that noisy neighbour impact. It is applied to all storage, and there is a difference. The internal workloads do get classified differently, so it makes sure that anything that's internal keeps ticking along, but your user workload will be classified differently, and that's where the rate limiters can kick in. There is a DMV which will tell you for each performance tier that you're running, what is your current limits. So as you scale up and scale down and query that DMV, you'll actually see the values change. Now, it is meant that predominantly as you double the DTUs, you should double roughly the resources available. Now, that works okay for the first few levels, but you will find that there's a tailing off, that you don't continually get to see the amount of increase that you would hope for. So there might become a balancing point where you need to adjust your workload until it gets to that bit of it's good enough and not really worth the extra expense to try and go to the next level for only a small improvement. And some of that might be because of the underlying IOPS and the physical storage. As I mentioned, transaction log rate governance is the one that's probably really going to hold you back and something you need to be aware of and be able to identify when it's happening. Where it will mainly hit you though is if you've got things like bulk inserts, select intos, index builds. These are the things that will generate probably the highest amount of transaction log entries. Now, it doesn't really matter on the IOPS on this. It really is the volume that's going through. And the reason for that is the guaranteed SLAs that Microsoft have. They have to ensure that they can continually take transaction log backups within the window they've defined to ensure you have your point-in-time recovery available. Now, the only way they can do that is to have a defined amount of volume going through on the transaction log within each window between backups. So that's when the transaction log rate limit comes in. It's applied during the actual log generation. So it's as you're actually creating that and pushing your queries through. So you will find that your whole queries slow down because they can't actually generate the transaction log first of all to be able to write that before then applying the data changes into your database. Now, where we want to look for that is going to be looking into your requests and your wait stats. And there is a wait stat that will explicitly identify the transaction log limits being hit. How can you mitigate this one? Well, it's a little bit more difficult. You can scale to a higher tier, but there is an absolute limit of 96 megabytes per second on the vCore instances. That's going to be slightly different on the DTU instances. And that's something you'll need to query the DMVs for to find out what's specifically in place there. But it will tail off and hit that absolute maximum. When you're doing bulk loads, you might want to consider loading into TempDB first of all, particularly if it's going to be transient data. So if you're going to load something in and then further process it before loading it into the final destination tables, TempDB is a great destination for that because it's minimally logged and it doesn't have the same impact through the throttling. So you might have to change your patterns there to make sure you get the benefit from that. You may also want to look at seeing if you can load it into cluster column store indexes. Does that suit your workload? Does it suit your data types? Does it suit your table? You do get a corresponding increase in CPU again with that, as we mentioned previously with compression on row and page level. Again, the overhead there will add some CPU overhead, but if you're being throttled by the log rate as is, it means that your I/O is going to be your main limit anyway, and what's slowing you down, and not CPU cycles. You probably have a few cycles to spare that you can allocate this way to give you that improvement. So we'll have a look at how that impacts over a couple of different sizes of databases. So we'll see the difference between a low-end one and a high-end one. And we'll see how that is manifested through the wait stats by doing the same activity on both databases. And you'll see the difference in performance between those. So how can we find out about what the transaction log throttling is like on our Azure SQL database instance? Well, if we use the DM user DB resource governance, DMV, we can actually query that, and using the max log rate and the max I/O, we can get the corresponding information. So I'm going to connect onto my log rate database and run this. So the important things to consider on here are, first of all, that we're running at an S1 tier, and that gives us a max log rate of 1.5 megabytes per second and 48 IOPS. So let's copy that across, and we'll save that up in here, and we'll compare it with our other database. So if I copy now into my other log rate database, and let me just comment that so we can run it again. Let's execute that. This time we're now running on an S12 tier. And the corresponding difference with that is that it now allows us 22 megabytes per second on our transaction log rate. So we can see that's a massive jump up of 20 times on the S1 tier. The number of IOPS also is significantly increased from the S1 tier as well. So now we'll run some activity onto our database and show that it is indeed the transaction log that is the rate limiter on this activity. What we're going to do is just copy from one of our tables into a new table, something that will generate a fair bit of transaction log. While we're doing that, the other bits that we'll track is the wait stats that are happening while that query is running. And I'm going to be using just a set of queries and tables from SQL Skills that are going to capture that for me and track the wait types, filtering out any of the benign ones, and give me the picture of things at the end of it. Now this will take about a minute or so to run the whole query. So what we'll do is we'll kick it off, and we'll come back onto the recording once it's finished. Okay, so we're back from this one. We can see that it is indeed the log rate governor that has been the predominant wait type while that's been running. So much so that it was actually 99.35% of all the waits during that query running there. So we can see that at this level in the S1, it very much is the biggest level of restriction. So again, let's take a note of that, those results. And now let's switch back over to our other log rate database. and we'll rerun the queries in here. So as we can see, this is now running on the S12, and that came back so much quicker as well. Now, although we can see on here, there is still some instance of log rate governor, but it has now dropped significantly down. It's only now hitting about 75–76%. So that closes off what I want to talk about today. We'll open it up for any questions, and thank you for all attending. But before we do, I just want to ensure that we give out the thanks to Microsoft for supporting the Data Platform Summit events. Thanks to everybody there. And a reminder that for you as well, you can win a prize by posting a selfie with hashtag DPS2020 and give us your session and conference feedback. Particularly for me to get some feedback from you as to how this went. Make sure that you still, even though it's a virtual event, visit our sponsors and exhibitors and follow everything that's happening at the event. So now I'll throw it open and see if anybody's got any questions.